Alright, Algebra 2, Lesson 34. Are all parabolas congruent? This lesson builds upon the previous lesson and applies transformations to show that all parabolas with the same distance between their focus and directrix are congruent. So I'll say that again. All parabolas with the same distance between their focus and directrix are congruent. So, opening exercise. Are all parabolas congruent? Use the following questions to support your answer. Draw the parabola for each focus and directrix given below. So we know our vertex is halfway between the focus and the directrix. And we need some points. So if I go over 2 from the focus and down 2, I'm at the directrix. So I know that that is equal distance, so it has to be one of my points. And I can do the same thing over here. Over 2 and down 2 is another one of my points. So now I have my parabola. Over here, the vertex is in between the focus and the directrix. And I'm 1, 2, 3, 4 away. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And I have my parabola. So what do we mean by congruent parabolas? Two parabolas would be congruent if we could find a sequence of rigid motions that takes one parabola onto the other. We could translate the vertex of the first one onto the vertex of the second one, then rotate the image of the first one so that the directrixes are parallel and both parabolas open in the same direction. If the transformed first parabola coincides with the original second parabola, then the two original parabolas are congruent. Are the two parabolas from part A congruent? Explain how you know. These two parabolas are not congruent. They have the same vertex, but different y values for each x in the domain, except for point 0, 0. If we translate the first one somewhere else, then the vertices will not align. If we reflect or rotate, then both parabolas will not open upward. There is no rigid transformation or set of transformations that takes the graph of one parabola onto the other. Are all parabolas congruent? No, we just found two that aren't. Under what conditions might two parabolas be congruent? Explain your reasoning. Once we align the vertices and get the directrices parallel and parabolas opening in the same direction, through rotation or reflection, the parabolas will have the same shape if the focus and the directrix are aligned. Thus, two parabolas will be congruent if they have the same distance between the focus and the directrix. That's important because that's how we draw the parabola. So if they have the same distance between the focus and the directrix, that means they'll have the same vertex and the same points. The x's and y values will be the same. Exercise 1.5. Draw the parabola with a given focus and directrix. You just need a really simple ruler to do this. It's hard to do it on here. So first I want to find the midpoint of this segment. It's right there. And then I know my first point, the distance here and the distance there has to be equal. And if you have a simple ruler, you can do it. Which is why I put this picture in here. So this distance and this distance are equal and equal, so you can draw your parabola pretty easily. Sorry, oops. I guess I didn't need to delete that. Draw the parabola with the given focus and directrix. Okay, the distance here is equal, so that's where the vertex is. And then you want the distance there to be equal, which is much easier to do with a basic ruler. And last one. About halfway through. That's terrible. And then our distances are about equal. What can you conclude about the relationship between the parabolas in exercises 1 through 3? The parabolas are all the same size and shape because the distance between the focus and the directrix stayed the same. These parabolas should be congruent. It looks like they're just rotated here and there. But yes, they should be congruent. Number 5, let P be the number of units between the focus and the directrix as shown. As the value of P increases, what happens to the shape of the resulting parabola? So let's look at this. P is this whole distance right here. So we have half of P and half of P. It says as the value of P increases, what happens to the shape of the resulting parabola? Let me type it out really quick. Hold on. So as the value of P increases, the graph is dilated and shrinks vertically compared to graphs with a smaller value of P. It appears to get flatter, and we're going to see how this works with a few examples. So let's do an example and talk through what's going on with our graphs. So example 1, derive an equation for a parabola. Consider a parabola P with a distance P is greater than 0 between the focus with coordinates 0, 1/2 P. So there's our focus with those coordinates. And directrix with y equals negative 1/2 P. So I'm at the x-axis. My focus is half of a P distance above the x-axis, and my directrix is half of a distance of P below it. What is the equation that represents this parabola? So let's work through it. What are the coordinates of the vertex? The vertex is 0, 0. So let's find the formula for the distance between the focus and point xy. So our focus is, I don't know why that E is on there, sorry, 0, 1/2 P, and a point on the line is xy. So using our distance formula, we have x minus 0 squared plus y minus 1/2 P squared. Okay, now, so that's something we're looking for. This is what we did last lesson, right? Now I need to find a formula for the distance between xy and the directrix. Distance between xy and the directrix. So we're looking for the distance between the point xy and the directrix. We have y plus 1/2 P. What you see right here. So the distance between the point xy and the directrix is y plus 1/2 P. Let me box that. Since those two distances are equal, we set them equal to each other and solve, which I'm going to do on the next page. So I have y plus 1/2 P equals square root x squared plus y minus 1/2 P squared. Let's go ahead and square both sides. We have y plus 1/4 P. That's not right. Sorry, I'm squaring both sides. Okay, I had to erase that. That took me longer than it should have. So let's square both sides. That gives me first times first is y squared plus 1/2 P plus 1/2 P is P plus 1/4 equals x squared plus, let's square that, y squared minus P plus 1/4. Oh, P squared. That's what I'm missing here. P squared. Yes. Okay, the y squareds cancel out. Found another mistake. let's see. So the y's cancel out. I'm left with 2py, and those cancel out also. I add this over. So 2py equals x squared. Y equals x squared over 2p. Let's write that a little bit neater. Y equals 1 over 2p x squared. So that's my parabola equation. The parabola big P equals all points x and y such that y equals 1/2 p x squared. Cool. Really quick, let's talk about what we wrote in the last number 5. So go back to number 5. It says, as the value of p increases, the graph is dilated and shrinks vertically, compared to graphs with a smaller value of p. So how does this equation verify the conjecture that as p increases, the parabola gets flatter? I'm going to do a few graphs with Desmos and see if we can see the difference. And I'm going to be graphing this equation right here. So here we go. You'll see the graphs get flatter and flatter. This is when p equals 1, pretty tight. P equals 2, I get 1/4. It's getting a little wider. P equals 4, I have 1/8, even wider. It shows the trend. It would get wider and wider as p gets larger. Okay, these next 2 slides are quite a bit of reading. If you could read through them, it gives some terminology that's important. Let's see, we have shown that any parabola with a distance of p greater than 0 between the focus and the directrix has a vertex at the origin and is represented by a quadratic equation of the form 1 over 2p x squared. We're going to use that form a lot today. Suppose that the vertex of a parabola with a horizontal directrix that opens upward is hk. So this is your vertex, hk. And the distance from the focus to the directrix is p greater than 0. Then the focus has coordinates h, k plus 1/2 p. The directrix has equation y equals k minus 1/2 p. If we go through the above derivation with focus h, k plus 1/2 p and directrix y equals k minus 1/2 p, we should not be surprised to get a quadratic equation. In fact, if we complete the square on that equation, we can write it in the form y equals 1 over 2p times the quantity x minus h squared plus k. Okay, this is pretty darn important in parabola math also. In Algebra 1, Module 4, Topic B, you guys didn't use this curriculum when you took Algebra 1, or you may or may not have, I guess. We saw that any quadratic function can be put into vertex form. Okay, it's by completing the square that you do that. Now we see that any parabola that opens upward can be described by a quadratic function in vertex form where a equals 1 over 2p. Rewind a little bit. This vertex form, this is completing the square. Like we said, anything can be put into vertex form, and it allows us to compare parabolas without drawing them, to compare them to see if they are congruent or similar or anything. Because when they're both in the same form, you can actually compare them a lot easier. If the parabola opens downward, then the equation is y equals negative 1/2 p, or 1 over 2p, times x minus h quantity squared plus k. The negative makes it open downward. We still have vertex hk, distance p between the focus and the directrix, and opening downward. Let's move on. We're going to utilize this information in the upcoming slides. Vertex form of a parabola. Okay, right here we have opens upward. Here we have opens downward. Okay, that is if p is greater than 0. Our vertex is HK, distance P from focus to directrix. What else do I need to point out? Opens downward with vertex HK and distance P from focus to directrix. Oh, here we have, if it starts with an X, and it's Y minus K quantity squared, we open to the right. Negative, we open to the left. Yep, I think that's great. So let's use this information in the next slide. Okay, the graphs of y equals 1/2 x. That's in blue, so maybe I'll put it in blue. Let's do that. In this example, p equals 1. And another parabola in red are shown in the coordinate plane. So let's describe a series of rigid transformations that map the red parabola onto the graph of y equals 1/2 x squared. If we look at the first one, there are lots of different sequences of transformations that can take the red parabola to the blue one. For the graphs over here, looks like if I move vertically up 1 and to the left 1, then I would reflect over the x-axis. The red graph would be on the blue graph. So I'd move it vertical 1, positive 1, and then to the left 1, and then reflect over the x-axis. The transformation would take the red parabola onto the blue one. For the graph over here, again, I'm trying to get the red one onto the blue one, I could rotate, oh goodness, rotate the red parabola 90 degrees counterclockwise about the point -3, 0, and then translate the graph 3 units to the right. So if I rotated it counterclockwise about the point -3, 0, and then translated it 3 units to the right, the red parabola would be on the blue parabola. Okay, so that proves that they are congruent just by some rigid transformations. Okay, so basically no matter where the parabolas are on the coordinate plane, the parabolas are congruent. How do we know the parabolas are congruent? It's the distance between the focus and the directrix is what tells us that the graphs are the same. Let's write that down. So the distance between the focus and the directrix for the parabola y equals 1/2 x squared is 2 units. As long as this is true, the parabolas are congruent. Okay, we're going to lovingly skip this proof. Okay, we've done a lot of the proof involved here just by doing the rigid transformations. So let's go ahead and use what we've done and start working with some problems. So exercises 6 through 9. Let's reflect on our theorem about parabolas. So first of all, restate the results of the theorem from example 2, which was the proof that we skipped. So we'll do this together in your own words. So all parabolas have the same distance between the focus point and the directrix. They're congruent. So as long as your distance between the focus point and the directrix is the same, then the parabolas are congruent. Create an equation for a parabola that is congruent to y equals 2x squared. Explain how you determined your answer. So if you got the parabola y equals 2x squared, we just need to translate that somewhere. So if I take that same equation and I add 1 to it, I just moved it 1 unit up. If I take the equation, I just took the original equation and moved it 3 units down. Should probably make that legible. Okay, so the parabolas are congruent because that is equal. We're just translating it left and right, or sorry, up and down. Create an equation for a parabola that is not congruent to y equals 2x squared. Explain how you determined your answer. So if we're starting out with y equals 2x squared, if I change the distance between the focus and the directrix, then I'm changing my parabola. It's no longer congruent. These are all going to be different. Yes, my variable ending is the same, but my p value is not the same. Therefore, the distance between my focus and directrix are not the same. Write an equation for 2 different parabolas that are congruent to the parabola with a focus of 0, 3 and a directrix line of y equals -3. So 0, 1, 2, 3, and y equals -1, 2, 3. So what is my distance here? My distance is 6. So 1 over 2p equals 1 over 2 times 6 is 1 over 12. So an option would be 1 over 12 x squared, okay, I don't know, plus 1, and 1 over 12 x squared. If you graphed those, you would be on the origin going up. Okay, that is this equation, and the plus 1 would just be your vertex translated up 1 unit. Your focus would also transfer up, and your directrix would also transfer up. Okay? Goodness, that's it. That's our last slide. All right, we're going to practice this on your problem set, and it's going to be awesome.